Okay, so the first thing we'll talk about is aortic stenosis. Okay, so this is the left ventricle. Okay, when this left ventricle contracts, it sends blood, oxygenated blood through your body. Okay, and there's a valve here. There's an end-on view of the valve. Okay, and when the left ventricle contracts, this valve opens and the blood gushes out to the aorta. Okay? Now, so this is a healthy valve and it'll open like this. And when it's diseased, so it's not able to open fully. Okay? So let's see, here's what happens. Okay. So you saw that, so this is the equation of continuity. What this says is, the equation of continuity says A1 times V1 equal to A2 times V2. What this formula says is how many gallons a minute of blood are flowing, or how many liters. Okay, so this is the volume of blood that is flowing per second. Okay. What this is this is the area of cross section, and this is the speed of the blood. Okay. So what this equation is saying is that if the area narrows, then the blood speeds up, or the fluid speeds up. Okay. So when this heart contracts, it's speeding up the blood. And if the valve is narrow, on the downstream, this blood will be going, if this is narrow, if this area is small, the blood will be going much faster. Okay. Now, in a hospital, a doctor can't see these valves. What they can do is they can measure the speed of the blood before the blood enters the valve and after the blood goes past the valve. And if the valve is too narrow, the blood downstream is going much faster. Okay, so what doctors can do is measure the speed of the blood here and measure the speed of the blood here. Okay, so if this blood is flowing too fast, that means this valve has narrowed. And that's how they know about disease. Okay, that's how they know, they can tell if the valve has gone bad. Okay, and the speed of the blood is measured using echocardiogram. Okay, so it's a Doppler, it works on the Doppler effect, just like how the cops catch us using a Doppler effect. And that's how they measure your speed. Okay, so the same thing is done here. Okay, so they can measure these speeds using echocardiograms, and from that surmise if your valve is diseased. Okay, if your valve is diseased, it's not opening completely, and this blood is going too fast. Okay. All right. Here's another equation that we saw, Bernoulli's equation. P1 plus 1/2 So 1/2 rho V1 squared Okay, this is Bernoulli's equation. What this says is the pressure at a given location, pressure at one location, plus this is the kinetic energy per unit volume. This is the speed of the blood. Okay, this term plus this term is constant. So pressure at one location plus this kinetic energy per unit volume is equal to the pressure at another location and kinetic energy per unit volume at another location. Okay, what this equation is saying is if a fluid goes faster, the pressure at that location decreases. Okay, so if this term increases, if this term is bigger, this term gets smaller. Okay, when a fluid is flowing faster, the pressure at that location is lower. All right, so the doctors say it this way. So here we're dealing with if a valve has gone narrow, then the blood is flowing faster. That means the pressure here has gotten lower. Okay? All right, so the doctors, well is, if this blood is flowing too fast, okay, if the blood is flowing faster, pressure drops. So if the pressure across the valve drops by 40 millimeters of mercury, then that means that valve has gone bad. Okay. So again, all the diagnosis is based on the blood flow measurements. Okay. So they'll measure the speed before the valve, and they'll measure the speed after the valve, and calculate the pressure drop. And if the pressure drop is a certain amount, then it's diseased. Okay. So here's a problem in your book. So in one patient at the left ventricle, as the left ventricle is ejecting blood, measurements show speed of 1.1 meters per second. Okay, so the speed here before the valve is 1.1 meters per second. And again, these speeds are measured using an echocardiogram, and then they measure the speed downstream. And the speed there is 3.5 meters per second. All right, so the speed here is 1.1 meters per second. The speed here is 3.5 meters per second. And so using this equation, you can calculate the pressure difference. Okay. And so so one of the diagnostic criteria is a drop in pressure as the blood traverses the valve. If the pressure drop exceeds 40 millimeters of mercury, diagnosis of severe aortic stenosis is warranted. That means your valve is diseased. Okay. So if these are the speeds measured, this calculation shows you, so there's the pressure drop, P1 minus P2 is equal to that. And so there's the density of blood, there's the speeds, there's the pressure drop in pascals, and that's converted to millimeters of mercury. Okay, so for this speed, the pressure drop is 44 millimeters of mercury. That means the blood has sped up too much and the pressure has dropped too much. That means the valve is diseased. Okay. So again, they can't see this valve. All they're doing is measuring the speeds of the blood here. And from the speed measurement, they know that their valve is diseased. Okay. So that's what that is. Okay. Now we'll take into account viscosity of a fluid. Viscosity is friction in a fluid. Okay. And you guys all know intuitively that which flows easier, water or oil? Water flows easier. So water's viscosity is less. And also for a fluid, if you heat it up, then its viscosity will increase or decrease. Decrease. Okay, so for instance, they use this. Okay, so when viscosity decreases, it's easier to pump a fluid. So for instance, if you wanted to pump honey from the ground level to a tank up there, it's much harder to pump honey than water, of course. Okay. And this happens in real life. So when they pump oil in Alaska, okay, in Alaska it's cold, and when the oil gets cold, the viscosity is quite high. So what they do is they put heaters around the pipe. They heat the oil, so then now it's less expensive to pump the oil. Okay? So the money spent on heating the oil is less than what you would have spent on pumping cold oil. Okay? So all this stuff has real world consequences. So a fluid's viscosity goes down when you increase the temperature. Okay? Viscosity is denoted by eta. And so here are viscosities. So for olive oil, the viscosity is, so there is viscosity, and this is in SI units. Okay, the viscosity of oil is almost 10 to the minus 1. This is, you can think of this as 10. 10 times that is 10 minus 1. And you see the viscosity of water is 10 to the minus 3. So the viscosity of oil, olive oil, is about 100 times greater than that of water. That means it's harder to pump oil, olive oil. It's 100 times harder to pump olive oil. Okay. So friction is greater. Okay, so we'll, viscosity of fluid's resistance to flow is a fluid's resistance to flow. The viscosity of a fluid decreases with an increase in temperature. Okay, and here viscosities of water at various temperatures at 20 and 60 degrees. Okay. All right, so if there was no viscosity in the fluid, then that fluid would flow in a pipe like this. Okay, the speed everywhere would be the same. Okay. Now, when there's viscosity present, the fluid is flowing the fastest here, and then gets slower and slower, and near the surface of the tube, near the inner walls of the tube, the fluid is almost at rest. Okay, the viscous molecules are grabbing onto the, so if this was blood is grabbing onto the walls, and the blood flow velocity is almost zero. Well, why would we care about that? Well, if the blood is flowing real slow here, all the plaque deposits can happen here on the walls, and plaque deposits can build up. If there was no viscosity, if it was flowing fast, then you wouldn't have plaque deposits. Okay, so for blood moving through arteries, the fact that the fluid at the outer edges lingers and barely moves allows deposits to build up on the inside of a wall. Okay, and then if you have plaque deposits, now you have problems. Okay. All right, so whenever they show you a flow like this, that means the viscosity is non-negligible. Okay, so what we do is, this is the flow rate, and we define something called an average velocity. You see the velocity of blood at different locations is different. Here it's slower, this blood is moving faster, a little slower, and so on. We'll define an average velocity for the blood flow, which is the flow rate divided by the area of cross-section. Okay. Now, viscosity is friction. Okay, okay, so here is this object. If I push this, it stopped. Why did it stop? Because of friction. Okay, so just like that, if it stops, so if you have a fluid that has viscosity, to keep it moving, you have to keep pushing it. So you have to maintain a pressure difference to keep the blood flowing. Okay, and we'll give you the equation for that. So if in viscous flow, something must apply a steady force equal and opposite to the viscous drag to push the viscous fluid through a tube. Okay, so that's a pressure. That force is the pressure. Okay, so if you have a viscous fluid, the friction force or the drag force is given by this. So 8 pi eta, that's the viscosity of the fluid, the average speed at which the fluid is flowing, times the length of the fluid. Okay, so the friction over that length of the tube is that much. So if you want to keep the fluid moving, then you have to, in that direction, the drag force is in this direction, so you have to apply a force equal to that in this direction. Okay, so the drag force is in this direction. You have to apply a force, okay, and that force comes from the pressure difference to keep the blood flowing. Okay, so the pressure difference you have to maintain is, so the force due to the pressure divided by the area should equal the drag force and divided by the area of cross section. Okay, so the pressure difference you have to maintain is given by that. Okay, so I'll write it here. Okay, so what this equation is saying, if you have a viscous fluid, to keep it flowing at that speed, you have to maintain this pressure difference across that length of the tube. Greater the viscosity, greater the pressure difference you have to maintain. Okay, harder your heart has to work, harder those pumps in Alaska have to work. That is money. Okay, so to save money when you're pumping oil in Alaska, what do? You try and reduce the viscosity. How do you reduce the viscosity? Heating the oil. Okay? Everything is about, if your heart is working harder, your heart has to work all your life. Okay? If it has to work harder, it won't work as long. Okay? All right, so that's what this equation tells you. Okay? All right, a large pressure gradient is needed to move fluid with greater viscosity. Okay, so you are trying to move the fluid through that length. The greater the viscosity, the greater the pressure difference you have to maintain. Okay. So Poiseuille's equation gives you, this is the flow rate. Okay. To maintain a flow, so this is how many gallons a minute you're pumping. This is the pressure difference you have to maintain. So the pressure difference per unit length. Okay. So this is called the pressure gradient. Greater the viscosity, greater the pressure gradient you have to maintain to get a given flow rate. Okay. So now this equation is important in understanding it. So there's the flow rate. This is the pressure gradient, meaning how much pressure is increasing per unit length. This is the viscosity, and that is the radius of the blood vessel. Okay. So now let's look at a problem. Okay. So the flow rate is dependent on the radius to the power 4. This is very important. So look at this. Here's plaque built up in somebody's blood vessel. So when the plaque builds up, what happened? The radius decreased. Okay. All right. If this radius decreased, the flow rate decreased. If the flow rate decreased, then you're not getting nutrients and oxygen to where it needs to go. So if the radius decreased, the flow rate decreased. What can you do to keep the flow rate up? You have to increase the pressure gradient. You can't change the viscosity of the blood. When you increase the pressure gradient, what happened? Your heart is working harder. How long do you want your heart to work? Yeah, all your life. You can't have your heart working all your life. I mean, your life shortens. Okay. So now let's look at the numbers. Okay. So let's look at this plaque buildup. Okay. What this problem shows you is, if the plaque builds up, okay, so suppose the diameter of the artery is reduced by 25%. So the diameter reduced by 25% because of this buildup. Okay. So this became 0.75, the original radius, the healthy radius of our heart. Okay. And the flow rate, when the radius is reduced to 75%, decreases to 32%. Okay, so again, that's right. Okay, the radius decreased by 25%, the flow rate decreased to 32%, 1/3 the amount of blood is flowing. Okay, so if this blood was going to your heart muscles, there's not enough blood going to the heart muscles to keep it healthy. All right, so this reduced, so you would have to increase the pressure. So now let's look at how much pressure you would have to increase to maintain that flow rate. And what this problem shows you is the amount of pressure you would have to increase is by 3 times, by a factor of 3. So what is your normal pressure? 120 when your heart contracts. You would have to, the pressure would have to increase to 360 millimeters of mercury if 25% plaque built up happened. You're not going to do that.
Overall, or just in the vicinity?
So in the vicinity. But you only have one pump. That pump has got to, so that pump has to increase the pressure here. So, okay, so let's go back. So this has to, the pressure here has to increase to 360 millimeters of mercury. This guy has to work 3 times harder. That's the only place. Uh, when the pressure increases by 3 times here, everywhere downstream it increases by 3%, but 3 times. All right. So you don't want this thing happening. Okay. You don't want plaque built up. Okay. Blood in veins. Okay, so I'm going to draw a simple diagram. So this is the heart. This is the aorta starting at the heart. When the ventricle compresses, it maintains a pressure of 120 millimeters of mercury. That's the systolic pressure. Okay. And we'll talk about this. And remember, blood is a viscous fluid. So to keep this blood flowing, the pressure drops as you're going down. And by the time you get to the veins, the pressure is dropped to 8 millimeters of mercury. So that's what this number is. Okay? So because you're having to keep the blood flowing, if the blood was non-viscous, if the viscosity was 0, the blood pressure would be the same everywhere. Okay? Yeah. So now let me ask you a simple question. You guys have gone to the doctor's office and they've drawn blood. Where did they draw blood from? I'm sorry? From a vein. Why don't they draw blood from the artery? Yeah. So it would sprout out like a hydrant, fire hydrant, because the pressure is higher. You draw blood out of a vein because the pressure in the vein is smaller and the blood is not gushing out faster. Okay? So even when they donate blood, that's where they get the blood from. Okay? All right, so anyway, blood samples are taken from veins rather than arteries because the pressure is much lower as the blood returns to the heart. Okay? Blood donors, so this problem goes through the details. So blood donors have a 6 millimeter long 16 gauge needle inserted into a vein in their arms. 6 millimeters is about that long. Okay? Blood flows through the needle, then 75 centimeters diameter tubing to the collection bag. Okay. So here's the flow rate. They're drawing half a liter of blood in 8 minutes. Okay. So when you're drawing blood from this vein, well, okay, it's not gushing out, it's coming slowly, and so it takes about 8 minutes to draw half a liter of blood. Okay. If they did the same thing from the arteries, you would collect the blood in 1/10 the time. Okay. The pressure is 10 times greater. If you collect the blood from an artery, you would collect the blood in 1 minute. But there's no room for error. It's gushing, and you would have to time everything perfectly. Okay, and okay. So there's the flow rate, and there's the flow rate in meter cube per second. The pressure across the needle. So we are using Poiseuille's equation. Okay, so the pressure across the needle. There's the flow rate, and so that's that equation, and there's the length of the needle. The pressure across the needle is that's what the pressure you would need to maintain the okay. And here's the pressure across the tubing. Okay, so the total pressure you need is about 8 millimeters of mercury. Okay, so you want drawing blood into this bag, collecting blood, and the pressure you would need from here to there is about 8 millimeters of mercury, and that's the pressure in the veins. Okay? So the bag is sitting at the same level as your arm. Okay, so that's what that problem says. Okay, so blood could be collected in 1/10 the time from a major artery with 10 times the pressure, but significantly higher risk. Okay? So you don't draw blood from arteries just because you don't want it gushing up. Okay? All right, now we'll talk about tiny organisms. Okay, so if it's very windy, you go walk on a windy day, and you can feel the force of the wind. Right? Now, on a windy day, next time, notice this. If you look at a leaf on the ground. Okay, and there'll be leaves on the ground that are not being blown away. Okay, so what's going on? Okay, so here is a fluid flowing. Okay. And let's say it hits a boundary like this. So it hits a ledge. Okay? And then what happens is the air, the fluid layer, this could be air, this could be water in the ocean hitting a ledge, this could be air blowing and hitting a ledge. Okay? So this air is not moving, and it's getting faster and faster. Okay? And then after a certain height, this is called the boundary layer, it has achieved the normal free flow velocity. Okay, so if you're a little bug and stuff like that, if you live here, then you don't feel any wind. Okay, you don't have to deal with the drag forces. If you're a little animal on an ocean floor, you don't have to deal with the tides and so on. Okay, so you don't get blown away. Okay, so organisms that reside in the boundary layer experience less flow and less drag than organisms in the free stream. This is especially true with toward the bottom of the layer. Okay, so let me. Okay. Terrestrial organisms no more than a few centimeters tall. So organisms living on land that few centimeters tall hardly know the wind is blowing. They spend their time in a quiet refuge with very little air motion. So as far as those guys are concerned, they never know that wind blows. Okay? So they don't have to deal with that. Aquatic organisms are somewhat more constrained, but staying below a few millimeters in height substantially reduces the drag from flowing past them. Okay? So they don't have to deal with that. Okay, so now let's look at the numbers. Okay, so this is called the boundary layer. The boundary layer is the distance over which the fluid has gained 90% of the free stream speed. Okay. So there is the boundary layer. And what we want to know is how thick that is. Why do we want to know how thick that is? So if you're an animal, if you're smaller than the boundary layer, if your size is tiny compared to the boundary layer, then you're not feeling the wind and stuff like that. You don't have to deal with drag forces. Okay. So, all right. So that's the boundary layer. Okay. So the boundary layer, the thickness of the boundary layer is given by that. There is viscosity, and that's how far behind you're from the ledge. Okay. The further you are from the ledge, the thicker the boundary layer. Okay. And this is the density of the fluid. This is the free speed, free flow speed. Okay. So greater the free flow speed, smaller the boundary layer. Okay. That's what that equation is telling us. For wind blowing at 10 to 12 miles an hour, this is fairly common. The boundary layer thickness from a few to 100 meters behind the lip, 100 meters is from here to building 100 or to the student center, okay, is a few centimeters. So the boundary layer thickness is about few centimeters. Okay, few centimeters is a few couple of inches. So if you're a bug smaller than a couple of inches walking on the ground, you don't feel the wind. Okay. It could be blowing 10 to 12 miles an hour, and you wouldn't feel the wind. Okay, so for a typical river current or an ocean surge, the boundary layer thickness is 1 to a few meters behind edge of a lip is a few millimeters. Okay, so that's a few millimeters. That's, let's say, half a centimeter. So you have to be really tiny not to feel an ocean surge. But anyway, that's the boundary layer. Okay. Terrestrial organisms no more than a few centimeters tall hardly know the wind is blowing. They spend their time in quiet refuge, like I said. Okay. All right, now we'll talk about turbulence. Okay. So whenever a doctor uses a stethoscope, what they're looking for is turbulence. This is turbulent flow. Okay, so let me get a better picture. Okay, this is turbulent flow. If flow becomes turbulent, then it's harder to pump the blood. Okay, if flow becomes turbulent, then so for instance in the aortic stenosis, if the blood is flowing too fast here, if fluid flows too fast, then it can become turbulent flow. And if flow becomes turbulent, then it's harder to pump the blood. Okay? You have to increase pressure to maintain the same amount of fluid flow. Okay? So turbulent flow is trouble. Okay? So in your body, everything is, all flow is laminar. Okay? And if there is turbulent flow, that means something is not functioning properly. So whenever a doctor is using a stethoscope, that's what they're listening for. They're listening for turbulent flow. Okay. So our analysis of both ideal and viscous fluids are assuming that the flow is laminar. Okay. So this is laminar flow. This is turbulent flow. Okay. When does a flow become, when does a fluid become from laminar, transition from laminar to turbulence? Beyond a critical speed. Okay, so as the fluid gets faster and faster, eventually it'll become turbulent flow. Okay, so what you want to do is you want to try and keep everything below a critical speed. Okay, so remember in that valve disease, if the valve didn't open properly, if the valve opened only a small amount, the fluid was flowing faster, and one of your concerns was you don't want the flow to become turbulent. Okay. Many flowing fluids exhibit turbulence. Turbulent flow is characterized by chaotic changes in pressure and velocity. Whirlpools and eddies and vortices are common, and this fluid is well mixed. Okay, so that's what determines whether a fluid has laminar flow or irregular or turbulent flow. Okay, so the Reynolds number will tell you whether the flow is laminar or turbulent. So for a fluid flowing through a pipe, the flow is laminar when the Reynolds number is below 2000. And when the Reynolds number is above 4000, for a fluid flowing in a pipe, the flow becomes turbulent. This is for a spear moving in a fluid. Okay, the flow is laminar as long as the Reynolds number is less than 1, and the flow becomes turbulent for Reynolds number greater than 1000. Okay. Now turbulence is not well understood, and this is hard to calculate, so these numbers are experimentally found. Okay. So the Reynolds number is the ratio of inertial forces to viscous forces. The characteristic size L is, so for a tube, that's the diameter of the tube. And for this spear, L is, again, the diameter of the tube. Okay, so the Reynolds number is the density of the fluid times the velocity of the fluid times the characteristic size. So in this case, that's the diameter of the tube and the viscosity of the fluid. So the greater the viscosity of the fluid, smaller the Reynolds number. Okay. Okay, so what we are concerned with is a fluid flow transitioning from laminar to turbulent flow. We don't want turbulent flow. So if in your body you have turbulent flow, then that's trouble. Yeah. So viscous fluids like honey tend to flow very smoothly, so we expect laminar flow for low Reynolds number. At high Reynolds number, when inertia dominates, flow becomes turbulent. So here's a good analogy. It's like a stampede of 1,000 closely packed cattle. It is smooth so long as every cow maintains absolutely the same velocity. But the slightest stumble causes the flow to break up into a chaotic mess. Okay? So as the Reynolds number increases, there comes a point where the slightest irregularity, even just molecular diffusion, can cause turbulence. So at high velocities, even the smallest disturbance can cause turbulence. Okay? So imagine a whole bunch of cattle running into a pen at high speed, and one stumbles, and what happens to the flow? Nobody's going into the pen. Okay. So there's no satisfactory theory of turbulence. Turbulence is not well understood. Okay. There's no way to predict the range of Reynolds numbers. Okay. So you get these numbers from experimental measurements. Okay. So again, what does this number tell you? This number tells you if this Reynolds number is below 2,000 for a fluid flowing in a tube, that's laminar flow. If the Reynolds number is greater than 4,000, that flow is turbulent flow. Okay. Now I'll show you the numbers for again. So again, Reynolds laminar flow when the Reynolds number is below 2,000, and turbulent flow when it's over 4,000. Okay. So blood flow is normally laminar, but some pathologies disrupt the flow and create turbulence. Okay, so disease pathologies will create turbulence. So like I said, when a doctor is using a stethoscope, they're listening for turbulence, and that indicates some pathology. Okay, yeah. The passage of air through your respiratory system is laminar at modest respiratory rates, but can become turbulent as the airspeed increases at elevated respiratory rates. Okay, when would this happen? Let's say you go for a very fast run for a long time, then you're breathing harder, and then the flow becomes turbulent. And if the flow becomes turbulent, then you're not, the flow rate is disrupted. The problem gets worse. You need more air, and because it's turbulent, you're getting less air. Okay, so that's bad. Turbulent flow is less efficient than laminar flow, which means a given pressure gradient generates a smaller flow rate. Okay, so a given pressure gradient will generate smaller flow rate. Oops, where is that problem? Okay, I guess that problem comes a little later. All right, so now we'll talk about the circulatory system a little. Okay. So here's your heart. Okay, so your heart really has two pumps. There's the right ventricle and the left ventricle. The atria are just, they're mini pumps, and they store the blood. Okay, so deoxygenated blood from the body has come to the right atrium. That gets sent to the right ventricle, which sends this blood to the lungs to get oxygenated. Okay, and then that blood from the lungs comes back to the left atrium, which gets sent to the left ventricle, and from here you send the oxygenated blood to the whole body. So that's the system. Okay, so oxygen depleted blood comes here, that gets sent to the lungs. From the lungs, the oxygenated blood comes back to the left atrium, which sent to the left ventricle, and then you have oxygenated blood sent to the whole body. Okay, why do you need oxygen in the body? Why do you need oxygen in the body? I don't a new slide for that. Where the heck is my slide? Okay, so let's figure out the reason for, okay. So oxygen allows cell to extract the maximum amount of energy from nutrients. Okay. Without it, cells must rely on anaerobic respiration, which is much less efficient and produce byproducts like lactic acid. So you need oxygen combined with nutrients. So these are your energy cells, ATP. Okay. So if you didn't have oxygen, you couldn't extract the maximum amount of energy from the nutrients, meaning you couldn't make as many ATP molecules. Okay. And so when you oxidize nutrients, you get more ATP molecules. Here's an amazing number. So after you use up the energy from ATP molecules, they become ADP, and then they have to be regenerated. Look at this number. You regenerate your body's weight worth of ATP every day. So if you're 150, 160 pounds, you're regenerating 160 pounds of ATP molecules every day. Okay? So that system had better not break down. Okay. All right, so let's go back to about every second your heart beats, and the contraction of the chambers of your heart send blood flowing through your body's arteries, capillaries, and veins. So we'll study the motion of the blood through your body. In larger vessels, the effect of viscosity is negligible. In smaller vessels, it isn't. Okay, so when they tell you your blood pressure is 120 millimeters of mercury, the systolic pressure, that the high number, that's the pressure here. Okay, at the heart, coming out of the heart. But that's not where they're putting the cuff. When they measure the pressure, where are they putting the cuff? Right there. They're putting it at the heart level. And so the artery that's coming, that's a big tube that's coming from here to there. And when blood flows in a big tube, the pressure doesn't drop much. Okay, so the pressure, I'll show you a problem. The pressure drop from here to here is about 1 millimeter of mercury. So when they measure the pressure in your arms at the heart level, that's proxy for pressure at what's coming out of the heart. Okay? So that's what that statement is. In larger vessels, the effect of viscosity is negligible. In the smaller vessels, it is not. But we'll come to that. Okay. The cardiovascular system consists of two pumps, the right and the left side of the heart. Okay. So this is the right ventricle, and this is the left ventricle. Which pump do you think is stronger? Which pump has to be stronger? This pump has to be stronger because it's got to pump blood through the entire body. This pump, what is it doing? It's sending blood to the lungs. Okay? Not that far. Okay. All right, so the and this pump has got to send through a longer pipe, so to speak. Okay? So this pump has to be stronger. Okay? Consists of two pumps and a complex arrangement of vessels that transport blood through nearly every part of the body. The purpose of a pump is to create pressure in the fluid. Okay, so when you compress, you're creating pressure. And what is the pressure? That's the pressure of the fluid when it's coming out of the aorta, 120 millimeters of mercury. Okay. So the right side of the heart pumps blood through the lungs to the left side again. The atria are reservoirs for the ventricles, which are the main pumps. So the ventricles are the main pumps. Okay. heart valves are open or closed by pressure differences across them. Okay, so when the left ventricle contracts, the pressure on, so the valve is not shown here, but the pressure here increases, and this valve opens. So for a valve to open, the pressure here has to be higher than the pressure here. Okay, and the valve will open and fluid will flow in that direction. And when the pressure here is higher and the pressure here is lower, then the valve will close. Okay, so pressured heart valves open or are closed by pressure differences across them. In addition, the valves between atria and ventricles are aided in opening by cords attached to the interior of the ventricles. Okay, so when the ventricle pumps blood out of the heart, the aorta balloons to take up extra blood. Okay, so when the ventricle contracts, it's pushing blood, and so these guys balloon to take the extra blood. Now, if as you get older, if these guys become stiffer and they're not expanding, then the pressure increases. So increase in pressure is also an indication of your stiffness of the blood vessels. Okay, so circulatory system. So the heart sends blood through all the major organs, supplies oxygen to them, and now the depleted blood with depleted oxygen and increased CO2 level comes back to the heart. Then it gets sent to the lungs where the carbon dioxide is expelled. Oxygen is brought back, and the new oxygenated blood goes back to the heart, and it's sent again to the system. So that keeps happening. Okay, you breathe in about 12 times a minute. Okay, so you're bringing in fresh oxygen, oxygenated blood about 12 times a minute. Okay, the major blood is pumped into the aorta, the large artery of the body, by the left ventricle. The right. Okay, so this just goes through the details of what I've said. Okay, so here's a picture that shows you the pressure. Okay, so you see blood coming out of the aorta is at 120 millimeters of mercury. This is for a healthy human. Okay, and by the time it gets here, the pressure is dropped to 85 millimeters of mercury. When it gets to your capillaries, it's 35 millimeters of mercury. Then at the venule ends, it's 15 millimeters of mercury. Okay, and by the time it comes to the heart, it's only 4 millimeters of mercury. Okay. Now it turns out that, let me show you this equation again. All right, so I'll point out an interesting fact. Where's my Poiseuille's equation? Oh, there it is. Pi r to the power 4, 8 eta. Okay. Okay, so let's say here's blood flowing. I'm just making up a number. 2 liters of blood flowing per second here. How much blood is flowing here? So 2 liters of blood is flowing out of the heart in a second. How much blood is flowing into the heart in a second? 2 liters a second, right? It's a continuous system. All right, so the flow rate is dependent on the difference in pressure. Okay, the flow rate is dependent on the difference in pressure. Okay, so the pressure difference between here and here is that much. Look at this, the pressure difference between here and here is much smaller. The pressure difference is much smaller, and the flow rate is the same. So how do you fix the problem? Okay, you could, huh? I'm sorry? Very good. So this blood vessel, the vein, is thicker than that. Why did you do that? Well, if this blood vessel was the same size as that, you would have to have the higher pressure difference. Your heart would have to work harder. Okay? So the body solves the problem by making this vein thicker. All right? So your body is very smart. Okay, and we'll look at that. Okay. So you can see the various pressures here, and you can also see the pressure with which the right ventricle sends the blood to the lungs is only 25 millimeters of mercury. That tells you this pump is not that strong. This pump has to be much stronger because the pressure it's creating here is 120 millimeters of mercury. Okay, so flow rate Q is the pressure difference divided by the resistance to flow. Okay. So, by the way, in this formula, R is resistance, and elsewhere it's radius. So that's in physics, they use the same letter to mean different things at different locations. Here it's resistance, and in another formula it was radius. Okay, so the resistance to flow is 8, the viscosity, the length times over pi to the power 4. Okay. So there's only a small pressure drop in the venous system from the capillaries to the heart. So here's what I was saying. See, the pressure drop from the venous system to the heart it drops from 15 millimeters to 4 millimeters, only 9 millimeters of mercury drop. This is because the 2 major veins returning to the blood to the right side of the heart are much larger. Okay, so these guys are much larger, and so you don't need as great a pressure difference. Okay, so if the radius is large, the pressure difference can be smaller, okay, for maintaining the same flow rate. The right side of the heart increases blood pressure to pump blood through the lungs. So here, this pump increases the blood pressure from 0 to 25 millimeters of mercury. Okay. And the left side increases from essentially 0 to 120 millimeters of mercury. Lung resistance reduces the pressure again. Okay, so this has reduced it to increase the pressure to that, and by the time it's coming out of the lungs, see, the pressure is reduced to 8 millimeters of mercury. That's because of the resistance, okay, through the lungs. All right. What is the job of the blood? Why do you have this complex plumbing system?
Bring oxygen everywhere and take away carbon dioxide.
Yeah, take oxygen and nutrients to cells and take away waste products. How does this exchange happen with the cells? I'm sorry? Via diffusion. Diffusion is a very slow process, and it happens over small distances. Okay, so what your plumbing system has to do is, okay, the blood coming out of the heart is coming at about 30 centimeters a second. It's traveling a foot a second. If the blood flew by cells at that speed, there won't be time for diffusion. You got to figure out how to slow down the blood. Okay. So here's the relevant formula. So here's the pipe. Oops. Okay. So 1, 2. Flow rate is V1 times A1 times V1. A1 is the area there, equal to A2 times V2. Okay, so A1 is the area of cross section and V1 is the speed there. Okay, so this just tells you how many gallons are flowing in a second. That's how many gallons has to flow out a second. A2 is the area there and V2 is that. Okay, so blood coming out of the heart is going at 30 centimeters a second, roughly. Okay, and by the time it gets to the capillaries, it's moving at 0.03 centimeters a second. Okay, so if you divide this by 1,000, one, two, three. Okay, so this divided by 1,000 is that. So by the time you get to the capillaries, you have to increase the area by a factor of 1,000 to slow it down. And that's what happens. Okay, so you see the total area of cross section at the aorta coming out of the heart is 3 centimeters square, and the area of the capillaries is 1,000 times greater. That's how you slow down the blood. You increase the area of cross section. Okay. And then there's another purpose. So now you will see in a problem when the blood is flowing through the capillaries at that speed, and the capillaries are, each capillary is about 1 millimeter long. So the time spent in the capillaries at that speed is about 5 seconds. So you have 5 seconds to do whatever job it is that you were built to do, to exchange oxygen and carbon dioxide. Okay. And there's a capillary around, let's say, 4 to 5 cells. For every 4 to 5 cells, there's a capillary. Yeah. And so you're dumping carbon dioxide, oxygen and nutrient into the fluid that's surrounding the cells and taking away toxins and carbon dioxide from there.
So when you cut yourself just a little bit, it might take a few seconds to bleed, but when you cut yourself quite a bit on accident, that's why it bleeds really quick.
Let's say that again.
You can do a vein versus just giving the capillary.
Oh,
You can brush it on, just working on something, look down, it's not bleeding yet, but seconds later,
no, it's maybe when you're scratching, and if you scratch a small pipe, the blood is slowly dripping. You make a hole in a bigger pipe, it gushes up. Yeah. All right, so that's the important thing. The last mile is diffusion. Okay, maybe I didn't hear you properly. Okay, anyway, the last mile is diffusion, and you got to slow down your fluid to do that. So see, here's the crucial numbers. Okay, so the area of cross section increases by a factor of 1,000. Okay, when the area increases, the blood velocity decreases. Okay. So shown as a schematic outline of the, so here are what this shows you is the diameter, the area, and capillaries, the area, and the veins, venules, veins. Okay, so the cross section of the aorta is that, and the vena cava, the big, remember we said the area of cross section of the big vein has to increase, and you see it's twice as much. And so you don't need as great a pressure difference to maintain that fluid flow. Okay. So the veins, the largest vein is twice as, the area of cross section is twice as big as the aorta. Okay. So there's only a very small change in pressure across large arteries. The pressure begins to drop when blood enters small arteries. Okay. So when the pipe is wide, the pressure drop is small because the resistance is small. The pressure drop happens, you have a greater pressure drop happening when the blood vessels get narrowed. Okay. All right. Okay. So many of the blood's duties are performed in capillaries, including the removal of waste products and the transport of nutrients and oxygen to the cells. Capillaries are 5 to 20 micrometers in diameter. The processes of diffusion, osmosis, dialysis, and active transport happen across capillary walls. Okay, these are all those other terms are okay. Okay, what direction does diffusion happen? What is diffusion? So diffusion will happen across a membrane, and if you have higher to lower concentration, these molecules go from higher to lower concentration. Okay. Now, here's what do your kidneys do? I'm sorry? I'm sorry? Yeah, so what the kidneys do is they get rid of the bad molecules, right? Okay, so there is this is a diffusion happening. Here's the bad molecules going. What is preventing the good molecules from going? So, okay, so here's urea going, but what's preventing the glucose molecules from going? They're also going. Well, you don't want to throw away good money, right? Then what do? You spend energy to reabsorb the good molecules. That's right. Okay, that's active transport. So if you're trying to get the glucose from a lower concentration back into the higher concentration region, you got to save it. That's active transportation. Okay. You have to spend energy. When will you spend energy? When will you bring it back? If you're spending less energy than there is in the glucose molecules, then you'll bring it back. If you have to spend more energy, then you're not going to do that, right? Okay. So whenever there's a profit to be made, then you'll do it. Okay. So in your body, all that kind of stuff happens. So diffusion, osmosis, dialysis, and active transport happen across capillary walls. Okay. And incoming arteriole branches into capillaries. Okay, so pathways through capillary beds are often tortuous and interwoven, giving the body considerable latitude in determining how much blood flows to which organ. Most capillaries are 50 to 100 times longer than their diameter. Okay, so okay. So here's velocity of blood is much greater in the major arteries. Okay, so blood is flowing at about 30 centimeters a second than in capillaries. In capillaries, it's moving at 0.03 centimeters per second. Okay, so you had to slow down the blood by a factor of 1,000 so that now at this speed, you can exchange nutrients and oxygen. Okay. Blood velocity increases again when the capillaries rejoin to form the veins. Okay, so blood velocity increases again. So here, since this area of cross section is twice as much, the blood velocity here is half the blood velocity here. Okay, so if it's 30 centimeters a second here, it's about 15 centimeters a second here. Okay. So most changes in blood velocity are due to changes in area of cross section. Okay, so this flow rate tells you how the velocity changes. Okay, so we'll stop at this slide. The human body has 10 billion capillaries. Okay, it's necessary to have a low blood velocity in the capillaries and to have many capillaries to have effective exchange of substance between blood and the interstitial region by diffusion and related slow processes. Okay, so nutrients are dumped to interstitial regions, and about you have a capillary for about 4 to 5 cells. Okay? So you dump stuff in this fluid and then that gets absorbed. Okay? So the human body has about 10 billion capillaries, giving a capillary every few cells on the average. Okay? So that's what your plumbing is about. All right, we will start.